continuing on from where we left off last week, we're going to take a look at the RC series circuit, and then have a look at RLC in series, and a quick look at something called resonance. Yeah, and then after that we'll be on a division. Right. So if we take an RC series circuit, we've got an AC voltage passing a current through a resistor and a capacitor in series. Yeah, so there's one current. If we were to phasor diagram that, we've got in red here the current in phase with the resistor voltage. That would always be in phase. And then we have a capacitor voltage that is 90 degrees out of phase from down here with the current and the resistor voltage. And then you complete the parallelogram to get the overall voltage there. And if we draw that on a time versus voltage and current diagram, in blue there we have the voltage, and then the current in red is out of phase, okay, and it's actually leading the voltage. Yeah, so current leads voltage. Yep. So we also have an impedance triangle that has got R at the horizontal. Yep. XC 90 degrees minus 90 degrees, or minus pi over 2 radians. Yep. And then the resultant Z comes in there. Yep. At an angle alpha in this case. Yep. So that's an RC series circuit, and XC is equal to 1 over 2 pi FC. Boom. Yep. We have a 10 volt AC supply. Resistor. We look for total impedance. We've got, and it's all useful to sketch this impedance triangle. We've got R there, 5 ohms, C, we've got 5, There. Yeah. So remembering back from what we did last week, we just said XC is 1/2 pi XC, or 1/2 pi times 60 under 100 10 minus 6, whatever that can I do. .50. Now, if I remember rightly, when we done the other one last week, we looked at 2 methods. Or was that in the maths? I can't remember. We looked at you. That's where we are. So, having found XC, how can we find Z? By what method? Triangle, triangle. 2 sides. Yeah. Square root of r squared plus xc squared. Square root of r squared plus .97 ohms. Yeah. But we also want the angle. How can we do that? Again, looking at our triangle, we're interested in this angle in here. Yeah. We've been given 5. We've calculated the opposite. It would be normal there to use the tangent. Yeah. So the tangent that we minus 1 on the opposite side, 26.97 over 5. 1 degrees. And that's negative because we're below the line. Yeah. So therefore Z is equal to 26.97 ohms angle minus 79.5 degrees. Yeah. And then we could, if we wanted to, calculate the current. I is equal to V over T. That's 10 at angle 0 divided by 26.97 angle minus 79.5 equals negative what? No. 10 divided by 26.97. I got 0.37. Angle plus 79.5 degrees. And if we check that with civil, capacitive circuit, and the current's positive, that's leading the voltage. Yeah. Okay? Yeah? Happy for me to move on? Right. So what happens when we bring everything together? So, RLC series circuit. What happens now is we end up with a current, single current there, a VR in phase with that single current. Yeah. VL vertically upwards. Right, I'm going to lengthen that line a little bit up to where I think it's got to do this better. Okay, and then we've got VC vertically downwards, but equally under some conditions VC could be the longer one, VL is shorter. Alright, what we then have is a value, and that's going to be about here somewhere, that is VL minus VC. Yeah? And the resultant is made with that. Yeah? Okay, that is the V50 supply. Alright, if we do the impedance triangle, here's our resistance on the horizontal. Here's XL, sorry, 90 degrees up. XL is up. XC is down, yeah. We've got XC down, and we've got a value that is we could call it XT, it's equal to XL minus XC. Yeah, the result of the two. And equally, that green line, if XC was bigger, the green line would be going downwards, and overall XC would be negative. Yeah? And the resultant in here, Z, is made using the total, the combination of the XL and XC in there, and Z is there. And the principle that's to be remembered is that all of that is dependent on frequency. Because this bit is 2 times pi FL, and this is 1 over 2 pi FC. So as frequency changes, if you increase frequency, that line's going to get longer, and the XC line's going to get shorter. And that's going to drag the black one further and steepen the angle. If you go the other way, you'll get to a point where XL is smaller than XC, and that'll drag that red line underneath. Yeah? Okay? So it's all dependent upon frequency. Yeah? So if we have a look at an example circuit based upon that, room, 10 millihenries, and like that. 10 volts. Yeah. First of all, we can calculate XL equal to 2 pi FL, 2 pi times 60 times 10 to the minus 3 equals. We can also calculate XC by another 2 pi. See? So, as our ones we've already calculated, this was 26.5 volts, and this was 3.77. Yep. So now RZT is equal to the square root of R squared plus XL minus XC all squared. Yep. If our impedance diagram is like this, XL is relatively short, XC is the longer one, so that bit's negative. You've got to be a bit careful here, because squaring that term is going to get rid of the negative sign, but you've got to remember. So the diagram helps you with that. Yeah, this is XL minus XC. So you know your angle is negative. You need to be careful. Right, when you're doing it the manual way like this. Put the numbers in. R 5 squared plus 3.77 minus 6.5 all squared. Yeah, well that's come out too. Oh, what that in there? How'd you get a negative? Yeah. 23.27 volts. Yeah. And then the angle is equal to tan of a minus 1 of the opposite side, which is XL minus XC over over R. Stand to the -1 of 3.77 5 all over 5. Yep. Just like we added this inductor into the capacitor circuit we looked at earlier, and we can see what's different looks like now. Therefore, ZT is 23.27 ohms, angle -77.6 degrees. Okay, if we look back at the previous problem, there, our total impedance was 26 magnitude. 79. So you can see here, reduce the angle and reduce the overall impedance of the circuit. So what should it do to the current? Yeah? Reduced impedance means, yeah. So I is equal to V over ZT 10 angle 0 over 23.27 angle -77.6 equals, and I got 0.43 amps angle 77.6 degrees. Yep. We check that with civil. This circuit is still, although we've added an inductor, the circuit is still overall capacitive, and we got a leading current. Yep. Okay. Right. So moving on, final little bit. Series resonance. Series resonance happens at a particular frequency, a given RLC combination. When the inductive reactance XL and the capacitive reactance XC are equal to each other. So we already talked about, as frequency changes, one reduces, the other one increases. Yeah, there'll be a point where, a particular frequency, where XL and XC are equal to each other. Yeah. At that point, VL, the voltage across the inductor, and VC, the voltage across the capacitor, will be equal. Yeah. Because they're of equal impedance. So they've got the same current flowing through them. Therefore, they must be equal. We're going to do some calculations in a minute to show that. Okay. The overall impedance Z will be equal to R, i.e. that's the minimum impedance possible in an LRC circuit. I'll show that graphically in a minute. Yeah. And I is equal to V over R. So the current flowing is simply the voltage over the resistance. And it will be the maximum possible current in that LRC circuit. Yeah? Because if we look at our impedance phasor, we've got XL and XC of equal length. Therefore, XT is there. It's equal to nothing. Yeah? So, the only impedance in the circuit is the resistance R. Yeah? If we change frequency in any way, okay, yeah, we change frequency such that this line gets longer, I'm going to draw the impedance up that way. There has to be a longer line. Or if XC gets bigger, we'd go that way. So that must be the point where, when these two are equal, all we got left is resistance. We've still got XC and XL, but because they're 180 degree opposed, they cancel each other out. Yeah. And you'll see in a minute what that does in terms of voltage. Okay. Well, the example I've got on here, and I don't even know if it's on your note, but what I'm going to do is, instead of having these values, we'll go with the values we just now used, so that you can see the difference. So we have 5 ohms. What do we use for inductor? RLC series circuit, 10 millihenries. We use 10 millihenries in there, and we use 100 microfarads in there. Alright. I wouldn't get too hung up on too much depth about resonance. I just want you to understand that there is this point where they're equal to each other. Alright. So what we're saying is, at the resonant frequency FR, F resonant, yeah, XL is equal to XT. Right? So what we can say is, therefore, 2 pi FRL is equal to 1 over 2 pi FRC. Yep. Now, how can we get the two FRs together? Yeah. I'll tell you what there is. There's an easier way to do this, right? Because we can write, it's easier to rearrange it, and then you can come back to 2 pi FR later. We can also say omega L is equal to 1 over omega C. I'll put in brackets over here, omega, and we'll call it omega R, by the way. Let's just write that again. Omega R L is equal to 1 over omega R C. Just makes the maths rearrangement a bit simpler, where omegas are equal to 2 pi FR. Just simplifies the rearrangement, getting omega R on its own. Yeah? How can I get this omega R alongside that one? How would I get that up there if I wanted it up there? It's on the bottom, multiply. So if I do omega R times omega R, what do I end up with? Omega R squared L is equal to 1 over C. Yeah? Next, divide by L, so we end up with omega R squared is equal to 1 over LC, and then we square root both sides, so we end up with omega R is equal to 1 square root of 1 is 1, yeah, LC on the bottom, yeah, and now we can replace omega R, therefore 2 pi FR is equal to 1 over root LC, yeah, and then we want to divide by 2 pi, so therefore FR is equal to 1 over 2 pi root LC. Yep. So we can now calculate what the resonant frequency for this circuit is. 1 over 2 pi times the square root of 10 times 10 to the minus 3 times 100 times 10 to the minus 6. Putting that frequency back into the two formulas for XL and XC confirms that they are both the same. Yep. So now our ZT is equal to R square root of R squared plus XL minus XC squared. That's equal to the square root of 5 squared plus none squared. Yeah. Equals 5 ohms. So instead of 20 odd ohms, the resistance to current is now 9 ohms. Yeah. So I is equal to V over ZT, so 10 volts over the 5 ohms equals 2 amps. What I do want you to look at is VL is equal to I times XL, 2 times 10 ohms, 20 volts. Yeah. VC, I times XC, again 2 times 10 equals 20 volts. Both got different angles because that's got a negative, a positive angle associated with it. Yeah, that's got a negative, so they've both got a 90-degree angle associated with them. But look at their value. We're only applying 10 volts AC. We got 20 volts across the two reactive components. Now, if you start looking at mains voltages, yeah, and circuits with low resistance, you can quite easily, you're applying 230 volts, and the only resistance you've got is the resistance of the inductor and the conductors, 2 ohms or so. You can easily end up with like 120 amps flowing, right? what's that going to do to the... You're going to end up with voltages across those two components in the thousands of volts. And we look at that a bit more closely in the principles next year about the implications of that. If the circuit's designed for the current that we got when we weren't at resonant frequency, less than half an amp, right, and then you go and start passing 2 amps, you're in danger of cables getting too hot, open circuits, breaking the insulation, going over the working voltage of the capacitor, and so on. Yeah, so there's some uses of resonance, filter circuits and things, right, at low voltages and currents. But series resonance is not a good idea to be playing around with circuits that could be series resonant, because we'll look at examples at mains voltages where you got like 5,000-6,000 volts across. That voltage can't do any work for you, because the minute you try and draw any more current from it or try and do anything with it, it disappears. Yeah, but that will give you a nasty shock. Right? You don't mess around with series resonance too much with students, because unless you're careful about the component values, as long as you put a fairly high resistance in the circuit, you can demonstrate the action safely. But right. So the thing really to remember, if we're talking about resonance, that's the point where them two values are equal to each other. And you can always make that statement that you know at resonance XL and XC are equal, cancel each other out, and so all you got in the circuit is a resistance R. Yeah? So various different things happen in circuits when you add AC voltages to them. Alright? So that concludes